Welcome to this walkthrough of problem number 1384, rank teams by votes. In this problem, we'll explore how to rank teams based on votes using efficient algorithms. By the end of this session, you'll have a solid understanding of how to approach and solve this challenge. Let's get started. In this problem, you are tasked with ranking teams based on votes provided by voters. The votes are represented as an array of strings, where each string is a permutation of all the teams. Each character in the string corresponds to a team, and the order of characters indicates the voter's preference, with the most preferred team at the start and the least preferred team at the end. The number of teams is limited to 26, and they are identified by uppercase English letters. The goal is to determine the final ranking of the teams based on these votes. To achieve this, the ranking must follow specific rules. Teams with more votes for the first position will rank higher. If there's a tie in the first position, the votes for the second position are considered, and so on. If all positions are tied, teams are ranked lexicographically. The output should be a single string representing the teams in their final ranked order. Now, let's look at the input and output format. The input is an array of strings called votes, where each string represents a voter's ranking of the teams. Importantly, the length of each string is the same, meaning all voters rank the same set of teams. The output will be a single string that shows the teams arranged in their final ranking order based on the rules described earlier. Let's consider the first example to understand how this works. The input is votes equals ABC, ACB, ABC, ACB, ACB. The output for this example is the string ACB. Here's why. Teamer receives the most support for the first position, securing 3 votes, and is ranked second in the remaining 2 votes. Continuing with the explanation for the first example, Team C is the next strongest contender, as it is ranked second in 3 votes and first in 2 votes. Finally, Team E comes in third because it is consistently ranked third in all 5 votes. Based on this analysis, the final ranking is A first, C second, and B third, resulting in the output ACB. Now, let's examine the second example. Here, the input is votes equals WXYZ, XYZW. The output for this case is XWYZ. To understand this, we analyze the rankings for each team. Team X is ranked first in one vote and second in another. Team W is ranked first in one vote but drops to fourth in the other. Team Y is consistently ranked third, and Team Z alternates between fourth and second. In the second example, the final ranking is determined by comparing the votes for the first position. X remains ahead of W because it has the same number of first-place votes but higher overall consistency in the rankings. When there's still ambiguity, lexicographical order is used to break ties, but in this case, it isn't needed. The final output is XWYZ. Now let's consider the third example, where the input is votes equals ZMNAGUEDSJYLBOPHRQICWFXTVK. In this case, there is only one voter, so the ranking is directly determined by the order provided in the input string. Since no other votes are involved, the output is simply ZMNAGUEDSJYLBOPHRQICWFXTVK, identical to the input. Finally, let's review some constraints and edge cases for this problem. The number of voters, or the length of the votes array, ranges from 1 to 1000. Each string in the array, representing a voter's ranking, has a length of up to 26 characters, corresponding to the maximum number of teams. Importantly, each string contains all unique uppercase English letters, and all strings are of the same length. Some edge cases to consider include scenarios where there is only one voter, in which case the output is the same as the input order. Another edge case is when all teams have identical rankings across all positions, in which case the result is sorted lexicographically. Additionally, the number of teams can vary significantly, from just one team to the full set of 26 teams, depending on the input. To start, let's consider the brute force approach. The intuition behind this method is to generate all possible permutations of the teams and evaluate each permutation based on the votes. For every permutation, we calculate its score by iterating through the votes and summing up the rankings for that specific arrangement. Once we have the scores for all permutations, we sort them to identify the highest ranked one. However, the complexity of this approach is a major drawback. Generating permutations alone requires O(n), where n is the number of teams. On top of that, scoring each permutation involves m*n, where m is the number of votes. Combining these together, the overall time complexity becomes n*m*n, which grows extremely fast as the number of teams increases. Even with just 6 or 8 teams, the factorial growth becomes computationally infeasible. This makes the brute force method impractical for larger inputs due to the sheer computational demands. Now, let's shift to the optimized approach, which offers a much more efficient solution. The key insight here is that we don't need to evaluate all permutations. Instead, we can directly rank the teams by building a scoring system based on their positions in the votes. Here's how it works. First, we create a dictionary that maps each team to a list of scores. The length of the list equals the number of teams, and each position in the list tracks how often the team appears at that rank. Then, we parse each vote string and update the scores for each team according to their rank in the vote. Once we've processed all votes, we sort the teams based on their scores in descending order. If there's a tie in scores, we break it alphabetically by team name. This method is much more efficient, with a complexity of m*n for constructing the score dictionary and an additional n*log for sorting. Together, the overall complexity is m*n plus n*log n, which is far better than the factorial growth of the brute force approach. While the sorting step isn't linear, it's still manageable and ensures correct ranking. The optimized approach is our chosen strategy because it strikes the right balance between clarity, correctness, and efficiency. By using a dictionary-based scoring system, we can map votes directly to team rankings in an intuitive way. The sorting step ensures that ties are resolved deterministically, which is crucial for accuracy. What's particularly compelling about this method is the realization that we don't need to generate permutations at all. Instead, we pre-process the votes into a structured format that allows us to compare ranks directly, eliminating redundant calculations and reducing computational overhead. This strategy is robust, as it gracefully handles edge cases like tied rankings or uneven vote distributions. It's also well-suited to the problem's constraints, avoiding the pitfalls of factorial growth. With a final complexity of m*n plus n*log n, this approach is efficient, scalable, and relatively easy to implement compared to alternatives. To solve the problem of ranking teams by votes, we start by understanding the context. Each vote is a string representing the preference order of teams. Our task is to combine these votes to produce a single ranking that reflects the collective preference. If there's a tie in the rankings, we break it using lexicographical order. The algorithm begins with input parsing, where we take the list of vote strings and identify the unique teams and their positions within each vote. For example, given the input votes equals ABC, ACB, BCA, our goal is to produce a ranking of the teams, like ACB. Next, we initialize a data structure to store scores for each team. Specifically, we use a dictionary called team_scores, where each key is a team, and the value is a list of integers representing the count of votes the team received in each position. For instance, if there are 3 teams, the list will have 3 positions initialized to 0. This setup allows us to efficiently track and update the scores as we process each vote. Now, we populate the scores for each team. For every vote in the input, we iterate through the teams listed in the vote. Each team's position within the vote determines which count in its score list is increment. For example, with votes equals ABC, ACB, BCA, the first vote ABC means team A gets 1 first place vote, B gets 1 second place vote, and C gets 1 third place vote. After processing this vote, our team_scores dictionary looks like this: 1, 0, 0, B, 0, 1, 0, C, 0, 0, 1. Then, we move to the next vote ACB, where A gets another first place vote, C gets 1 second place vote, and B gets 1 third place vote. Now, the dictionary updates to 2, 0, 0, B, 0, 1, 1, C, 0, 1, 1. This process repeats for all votes, ensuring every team's scores are accurately tallied based on their positions across all votes. After calculating the scores, the next step is to sort the teams based on these scores. The sorting is performed in descending order of the counts, starting with the highest ranking positions. In cases where 2 teams have identical scores, we use lexicographical order as a tiebreaker. To achieve this, we use a custom sorting function that compares the score lists of teams. For example, with the team_scores dictionary from earlier, sorting the team's results in the order A, C, B. Here, A comes first because it has the most first-place votes. C and B have identical scores, so the lexicographical order decides their positions. Finally, the sorted team names are joined into a single string to produce the final ranking. In this case, the output would be ACB, which is the ranking that best reflects the collective preferences of all voters. Using a dictionary to store scores is an efficient choice because it provides direct access to each team's data. The list of counts for each position within the dictionary allows us to dynamically handle varying numbers of teams and ranking positions. Sorting the teams involves multi-level comparisons, where we first compare score lists in descending order and then apply lexicographical order as a tiebreaker. This ensures that the result is not only accurate but also consistent and deterministic. In terms of efficiency, the algorithm is well optimized. Constructing the team_scores dictionary involves iterating through all votes and their positions, which has a time complexity of O, n asterisk m, where n is the number of votes and m is the number of teams per vote. Sorting the teams is O, k asterisk log, k, where k is the number of unique teams. Combining these, the overall complexity is O, n asterisk m plus k asterisk log, k, making this approach scalable even for larger inputs. To complete the algorithm, we use a list to store the teams for sorting based on their scores and lexicographical order. This list ensures that the sorting process is straightforward and efficient. When considering edge cases, there are several scenarios to account for. If there's only one vote, the input vote itself becomes the output since there are no conflicts to resolve. In cases of tied scores, the lexicographical order ensures that the result is deterministic. When votes have unequal team counts, teams not appearing in a vote are treated as having 0 votes in all positions. Finally, if the input is empty, meaning there are no votes, the output is simply an empty string. These considerations ensure the algorithm is robust and can handle any input edge case gracefully. The solution begins by importing defaultdict from the collections module, which is used to create a dictionary where each key maps to a list initialized with zeros, representing scores for each rank position. The rank teams function first checks if the input list of votes is empty, in which case it returns an empty string. Otherwise, it initializes the rank_scores dictionary, where each team will be assigned a list of scores corresponding to its position in the rankings. The next step is to iterate over the votes. For each vote, we loop through the team's positions, and for each team, update its score at the corresponding position. By using negative values, subtracting 1, teams with higher preferences, lower positions, are prioritized naturally during sorting. The teams are then sorted using Python's sorted function, which considers 2 criteria, the rank scores, in descending order, due to the earlier negation, and lexicographical order as a tiebreaker. The sorting key uses a lambda function to prioritize rank scores, with lexicographical order automatically applied due to Python's tuple-based sorting. Finally, the sorted teams are concatenated into a single string to form the result, which is returned as the final output. Here, we begin by importing the necessary utilities for our solution. We define a solution class and the rankTeams method, which takes an array of votes as input. First, we handle the edge case where the votes array is null or empty by returning an empty string immediately. Next, we create a map to store the ranking scores for each team, where each team is represented as a character and its scores are stored in an integer array. The size of this array corresponds to the number of teams, which we determine from the length of the first vote string. To initialize, we iterate through the characters in the first vote and assign each team an empty score array. After initializing, we process the votes by iterating through each vote string and decrementing the scores for each team based on their position in that vote. Teams ranked higher in the vote will have their scores reduced more significantly since a lower score indicates a better rank. This ensures that teams with more top placements will be prioritized when we sort them later. With the ranking scores populated, we move on to sorting the teams. First, we create a list of all teams from the keys in the rank scores map. We then sort this list using a custom comparator. For each pair of teams, we compare their scores position by position. If their scores differ at any position, we use the difference to decide the order. If their scores are identical across all positions, we use lexicographical order as a tiebreaker by comparing the characters directly. Once the teams are sorted, we concatenate them into a single string to form the final result. Using a string builder, we append each team in the sorted list to construct the output string. Finally, we return this string, which represents the ranking of teams based on the votes. This approach ensures that we respect both the ranking scores and lexicographical order, providing a clear and deterministic result. In this problem, we aim to rank teams based on votes provided as strings. Each string represents a single voter's preferences, where the first character is their top choice, the second character is their second choice, and so on. Teams with more votes in higher positions will rank higher overall. If two teams have the same scores, we break the tie by ranking them in alphabetical order. For example, given the input votes of ABC, ACB, BCA, we start by initializing a data structure to store the ranking scores for each team. This is a default dict, where each team is mapped to a list of scores. Each position in the list tracks how many votes the team received for that specific rank. To simplify sorting later, we use negative values when populating the scores. At this point, the rank_scores dictionary is empty and ready to be populated. Next, we populate the scores based on the votes. For the first vote, ABC, we assign the highest rank to Team A, the second rank to Team B, and the third rank to Team C. This results in Team A having a score of -1, 0, 0, Team B with 0, -1, 0, and Team C with 0, 0, -1. For the second vote, ACB, Team A receives another first place vote, making its score -2, 0, 0. Team C receives a second place vote, and Team B gets a third place vote. Finally, for the third vote, BCA, Team B is ranked first, Team C is ranked second, and Team A is ranked third. After processing all the votes, the final rank_scores dictionary contains a -2, 0, -1, B, -1, -2, -1, C, 0, -2, -1. This structure now encapsulates how each team performed across all ranks. With the scores populated, we proceed to sort the teams. The sorting is done using two criteria: first, the ranking scores themselves, and second, lexicographical order as a tiebreaker. For our example, Team A has the highest ranking due to its two first-place votes, followed by Team B, and then Team C. Since there are no ties in the scores, alphabetical order does not come into play. The sorted order of the teams is ABC, which becomes our final output for this example. Now, let's consider a new example where the input votes are WXYZ, XYZW, ZWXY. As before, we start with an empty rank_scores dictionary. Then, for each vote, we populate scores for all teams. For the first vote, WXYZ, Team W is ranked first, giving it a score of -1, 0, 0, 0. Team X is ranked second, Team Y is third, and Team Z is fourth. For the second vote, XYZW, Team X receives a first-place vote, making its score -1, -1, 0, 0, and so on for the other teams. Finally, for the third vote, ZWXY, we update the scores for all teams based on their respective ranks in this vote. After processing all three votes, the rank_scores dictionary is updated to reflect the cumulative scores for each team. The final rank_scores after processing, WXYZ, XYZW, ZWXY, is W-1, -1, 0, -1, X-1, -1, -1, 0, Y, 0, -1, -1, -1, Z-1, 0, -1, -1. We then sort the teams based on the same two criteria, their ranking scores and lexicographical order as a tiebreaker. After sorting, the teams are ranked in the order ZWXY. This becomes our final output for this example. For the final example, the input is Z, Z, Z. Here, there is only one team, Z, which appears in every vote. We initialize the rank_scores dictionary and populate it based on the votes. Since Team Z is the only team and is ranked first in all votes, its score is -3, reflecting 3 first-place votes. With no other teams to compare against, Team Z is ranked first, and the final output for this example is simply Z. In analyzing the time complexity of our solution, we start with the initialization of the rank_scores dictionary. Here, each team is assigned a list of size k, where k is the length of a single vote string. Since this initialization happens lazily as we populate the dictionary, there's no upfront cost for setting it up. Next, we have the population of the rank_scores dictionary, which involves two loops. The outer loop processes all n votes, while the inner loop iterates through each team in a single vote, which has a length of k. During this step, we decrement the ranking score for each team based on its position in the vote. The total number of operations here is proportional to O and *k, as every vote and its positions are processed exactly once. This gives us a clear idea of the computational effort required for this step. Now, let's move to the sorting step. After populating the rank_scores dictionary, we sort the teams based on their scores and lexicographical order. Sorting involves T unique teams, where T is the number of distinct teams in the vote strings. Each comparison between two teams involves comparing their ranking scores, which are lists of size k. This takes k time per comparison. The sorting algorithm, typically timsort, has a base time complexity of T*log T for sorting T items. Since each comparison involves k operations, the total cost of sorting becomes T*k*log T. After sorting, the final step is combining the teams into a single string. This step is straightforward and takes linear time, T, as we concatenate the T-sorted team names. Summarizing the total time complexity, the dominant term comes from sorting, which is T*k*log T. Adding this to the O and *k operations from score population, the overall complexity becomes O and *k plus T*k*log T. In scenarios with a large number of votes, the sorting step typically dominates. Shifting our focus to space complexity, the primary contributor is the rank_scores dictionary. This dictionary holds scores for T teams, with each score being a list of size k. The memory usage for this structure scales as T*k. Additionally, sorting requires space to store the list of T teams and their scores. While sorting algorithms like timsort are often optimized for in-place operations, the additional space required is still proportional to T. Finally, the output string, which contains the rankings of the T teams, requires T space to store. When we combine all these factors, the dominant term in the space complexity is the memory used by the rank_scores dictionary, resulting in an overall space complexity of T*k. The additional space required for sorting or the result string does not change the asymptotic complexity. Let's compare this optimized approach to a naive or brute force method. A naive solution might involve repeatedly iterating through all votes to count the rankings for each team and each position. This approach would involve T teams, each requiring k positions to be evaluated across n votes. The resulting time complexity would be T*k*n, which is significantly worse than our optimized solution. By contrast, the current solution efficiently populates scores in a single pass through the votes, with a time complexity of and *k, and uses a well-optimized sorting step with T*k*log T. This reduces redundant computations and ensures much better performance, especially as the input size grows. Finally, let's analyze the best, average, and worst-case scenarios for this solution. In the best case, all votes still need to be processed, which requires and *k operations, and the teams must be sorted, which takes T*k*log T. Therefore, the time complexity remains consistent even in the best case. For the average and worst cases, the worst-case scenario arises when all n votes are distinct, and sorting requires full lexicographical comparisons between teams. Despite this, the time complexity does not change and remains and *k plus T*k*log T. Mathematically, the two dominant terms in the complexity are independent and additive, one from score population and the other from sorting. Typically, with T equals k and n equals T, the sorting step dominates when the number of votes is very large. This ensures that the solution is efficient and well-suited for the problem constraints. One common mistake when solving this problem is overlooking edge cases. It's essential to account for scenarios such as empty input, single-element arrays, or situations where multiple elements are tied for the same rank. Failing to consider these cases can lead to incorrect results, so always validate your solution against edge cases to ensure robustness. Another issue is the inefficient use of data structures. For instance, using a nested list instead of more appropriate options like a dictionary or a heap can significantly increase the time complexity. A common example is scoring votes with plain lists, which might lead to O(n) squared performance instead of the more efficient O(n log n) when using a dictionary. Additionally, some people ignore problem constraints, such as assuming the input size will always be small. This can result in choosing suboptimal approaches, like brute force methods, which can cause timeouts when n is large. Lastly, pay careful attention to tie-breaking logic. Mishandling scenarios like sorting alphabetically or resolving ties based on secondary criteria can result in solutions that are only partially correct. Always implement tie-breaking rules exactly as specified in the problem statement. Premature optimization is another pitfall to avoid. Jumping into optimization efforts before establishing a working baseline solution can make the code unnecessarily complex and harder to debug. It's always a good idea to start with a correct brute force solution and optimize iteratively once the basic functionality is in place. Now, when it comes to interviews, focus on fully understanding the voting system or ranking mechanism described in the problem. Be clear about how ranks or votes are scored, as many problems require aggregating rankings or frequencies and systematically resolving ties. Also, be ready to discuss the trade-offs between different approaches. For example, you might explain how a frequency-based approach using dictionaries is often more efficient than sorting permutations. One key aspect interviewers often look for is clarity in handling tie-breaking logic. Walk through your process step by step, showing how you resolve ambiguities. Lastly, proactively address edge cases during your explanation. This demonstrates thoroughness and helps reassure the interviewer that your solution is robust. There are several related problems that you can practice to deepen your understanding of this topic. For example, LeetCode 1366, which is also about ranking teams by votes, is closely related and offers a similar challenge. Other examples include LeetCode 692, which involves finding the top k frequent words, LeetCode 451, which deals with sorting characters by frequency, and LeetCode 332, which focuses on reconstructing an itinerary. Besides these related problems, it's helpful to understand the alternative approaches and their trade-offs. A brute force approach, where you generate all permutations and compute scores for each, is simple to implement but highly inefficient for large inputs since it has a time complexity of O(n). A more efficient approach involves sorting with custom comparators. Here, you score each candidate based on votes and sort them, but you need to carefully implement tie-breaking logic. This method has a time complexity of O(n log n). Another balanced option is using a hash map to store scores and a priority queue for efficient ranking. This approach strikes a good balance between clarity and efficiency, also with a time complexity of O(n log n). Key patterns emerge in problems like this that involve ranking, voting, or sorting. One of the most effective strategies is leveraging hash maps in combination with sorting or heaps. These data structures allow you to efficiently aggregate data and rank elements based on their scores. Additionally, mastering custom comparators is crucial, as they are a common technique used to handle tie-breaking rules. These comparators allow you to define specific criteria for sorting when elements share the same primary score. Finally, many variations of this problem require frequency analysis or aggregation, so becoming proficient with these techniques is essential. By recognizing and practicing these patterns, you'll be well equipped to tackle similar problems in the future. Great job on completing problem number 1384. We covered the key concepts, the algorithm, and its implementation. Remember to keep practicing and refining your problem-solving skills. Thanks for tuning in, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!